I'm going to kind of mix up some of my terminology here, and that's because I'm kind of giving an overview of the literature about how we come up with material accountancy strategies for molten salt reactors. So you're going to see kind of a mix of terms like significant quantities and inventory difference, and that's primarily because I'm just focusing on reviewing a wide range of literature. So it's important to note that liquid fueled MSRs are quite a bit different from what we have from traditional light water reactors, right? As far as coming up with material accountancy. If you're not familiar with material accountancy, that procedure is kind of what it says on the tin, right? It's accounting for your material. So in a light water reactor, it's kind of straightforward in that you have, fuel pellets. They're in these discrete fuel assemblies. During operation, you have the giant multi-ton lid that's on there and it's sealed. Burnup is well characterized. We've studied them for decades. We have well-validated computational tools. But when it comes to MSRs, it's a little bit more challenging, especially on the statistical end, to kind of ensure that and quantify your material. Your fuel's in a bulk form. Depending on your design, you might have these constant feed and removals. You have this constant depletion and decay that you have to account for in process, unlike the LWR, because you could potentially access the process during operation. Salt volume estimation. There's been several talks today that have talked about the chemistry, and if you take a sample of the salt, it might be have a high level of heterogeneity. Strong radioactive source terms. So all these things together kind of create this challenge for developing schemes to develop your material accountancy approach. So since the salt or the fissile material is in a bulk form, we typically are looking at relying on doing material balance calculation similar to a bulk facility, right? That means it's somewhat comparable from a material accountancy perspective to an enrichment or aqueous reprocessing facility or electrical reprocessing facility or something like that. So it's pretty straightforward. I mean, you just count up essentially everything that comes into your facility, everything that goes out, and the changes in inventory. And that number should ideally be 0. I'll talk about that a little bit more later. For MSRs, we do something a little bit different. Although you can kind of think about feeds and removals as input and output flows, we're not really going to do that, because one key factor that we have to do for MSRs is we have to account for changes in our relative fissile content and ascribe it to expected or not expected changes, right? So for example, if you have 3 kilograms of plutonium on Wednesday and then it's not there on Friday, well, you need a way to say that this was expected, right? Because it was just consumed through burnup in the normal operation, or somebody potentially like diverted that material, or the material is otherwise unaccounted for. So what we kind of decided that you would do for that is you would have to have some sort of calculated quantity, right? You would use something like scale to periodically calculate what your expected inventory is, and you'd have to compare that to what you've actually observed using a variety of measurement systems, right? And so in practice, this equation never comes out to be totally 0, because you have some sort of measurement uncertainty, right? And so this measurement uncertainty in your material balance, so that can either be called your sigma muff or your SCID, depending on what sort of regulations you're looking at, is an important factor in determining what your system performance is, right? So because of this, you can see that this was a nominal design that we looked at called the Rebus design. It's kind of proposed as a large scale commercial liquid fueled MSR, and you can see that although our inventory difference or our material balance is centered around 0, we kind of have this wide range, this plus or minus 2 sigma, where this uncertainty arises due to our measurements, and that's going to play an important role in our ability to detect material that's maybe gone missing. So in the past, we considered something like 6 different designs, and here's kind of a summary table. I'm not going to go through all of them, but we looked at different fuel cycle types, different neutron spectrums, different sizes. And the real challenge here is that, like an LWR, they have large fissile inventories, right? So even if you had the world's greatest measurement system and you could quantify your fissile material down to, even, kind of like destructive levels, like if you had some sort of ICP-MS system, something like that, where you actually took it to the lab and did destructive analysis at, 0.25%, that still might not be enough to get a material balance uncertainty that's on the order of your regulatory targets, right? Depending on who that is. And so that's kind of the key challenge here is that, traditional material accountancy is probably not going to work for large scale commercial reactors in the traditional sense of hitting some sort of SEID target or a sigma muff or something like that. So what I'm going to do here is go through kind of a couple papers where the community kind of thought about different ideas about how we might ensure that these reactors are operating as we expect to kind of tee up some of these subsequent papers that actually present a MC&A approach for liquid fueled MSRs, because inevitably there's going to be questions about, hey, didn't you think about the off gas? Didn't you think about, the pressures and the temperatures and the powers, and that was kind of brought up in the previous talk. And the short answer is yes. And so I'm going to talk a little bit about a couple of papers that have been done that looked at these different things. So the first paper is a paper out from Penn State where they looked at the MSDR and they looked at just using fission products directly, right? So if you had diversions of material from your core from the MSDR, could we detect that, and how does that stack up against the nuclear data uncertainty, right? And so the short answer is they kind of looked at a loss of roughly 80 kilograms of plutonium from the MSDR, which is, again, a commercial sized reactor, and they compared it against what is the change in key isotopics and how does that compare to the nuclear data uncertainty. And the answer is it was pretty comparable to the nuclear data uncertainty. So and that means in practice, if your change is comparable to the uncertainty, you can't make a statistically conclusive statement about that sort of change. And so that's kind of a challenge, right? That means that 80 kilograms of plutonium in this reactor just walked away, and we can't statistically conclusively say that it walked away, right? So in practice, you do have some gains, right? So, like in light water reactors, they do calibrate the cross sections to kind of reduce that nuclear data uncertainty. But even then, that might not reach the uncertainty targets that we need. So there's a second paper from Penn State that, again, kind of looked at, well, instead of looking at the masses, could we just directly look at gamma ray spectroscopy of the salt, and how, can we do that? And maybe we can ignore the nuclear data uncertainty and say, okay, we're going to fix that later, but we're just going to look at kind of like the raw gamma spectroscopy. Turns out that's not going to work either. The changes in the peak counts, even when you neglect nuclear data uncertainty, are not significant enough to make a statistically confident statement that 10 SQs of material has been removed. So an interesting paper that University of Tennessee did, they said, okay, well, maybe there's something in the neutronics themselves that change. So Wheeler did this paper where they looked at if we did a periodic reactivity insertion, would there be a change in the frequency response if you removed plutonium from the system? So specifically, I believe they looked at the MSRE. So that inventory is a little bit smaller than some of the other designs that we've considered, and the fissile inventory of plutonium was on the order of like tens of kgs of plutonium rather than potentially hundreds for some of those other ones that I showed earlier. And so you can see here, I thought this was actually quite promising. You do see this frequency response. So I think they had a sinusoidal insertion of just a few PCM every so often. And you can see that, again, you can see some change, but again, to see these big responses, you had to remove significant portions of the total plutonium inventory, right? So even the smallest amount that they considered was on the order of like a 10% removal of the total plutonium inventory, which again is quite significant and might be insufficient for current regulatory targets. So work that I did recently is I kind of took the idea that, reactor vendors, they're going to need to know pressures, temperatures, pump speeds, things like that, just for their normal operation. Maybe we could leverage that, right? So if you remove material, kind of building on Wheeler's work, saying you're going to see something change in the neutronics, maybe that's like a reactivity insertion of some sort. Could we actually see that, right? So I took an existing model from the University of Tennessee. They have a dynamic process model. I coupled that with scale and sampler. If you're here for the lunch talk, some of the capabilities that they mentioned for molten salt reactor modeling, I use those to kind of look at what does a reactivity insertion look like when you remove material, and then how does that impact, some of the downstream thermal hydraulics. So I considered in this work 2 different approaches. I considered a machine learning approach and a non-machine learning approach, and the details for why those are what they are kind of explained in the paper. But the short answer up front is that even monitoring things like pump speeds, pressures, temperatures, you're still limited by your measurement uncertainty. So it really needed to be that, you had to measure temperature, pressure within 1% or higher accuracy, right, to have a reasonable chance of detecting a lot of these different losses. And if you had something as high as, 5 or 10%, it was just measurement uncertainty. A lot of these scenarios were just kind of off the table. So I just kind of want to sum up here again to kind of, show why the subsequent talks are going to present what they are, is that SEID alone or sigma muff is probably not going to be sufficient to reach, conventional regulatory targets. Aqueous facilities, for example, have the advantage of having like a accountancy tank where you can just have like all the material has to go through it. You can measure kind of like a small amount at a time, get the uncertainty down. But when you have these large scale commercial reactors, again, with, potentially tens, hundreds of kgs of fissile material, again, that's, pretty normal in the reactor space if you compare it to an LWR, but because it's dissolved in the salt, it's a little bit trickier to kind of deal with. There's been papers that looked at fission product indicators, both direct mass and the gamma spectroscopy. There was neutronics-based techniques. Maybe that could work for, kind of a process monitoring type approach, which would be more relevant for international safeguards. And, more recently, I kind of looked at things like looking at temperature and pressure to kind of, again, this process monitoring approach that's more amenable to international safeguards to see, could we at least have some indicator that the material might be missing. So yeah, that's about all I've got. And so, yeah, the next